So in this paper, we propose the macro mini linear actuator for active bodyweight support system. We know that we need a high force system that can carry the human weight, and sometimes we require the high drivability in the system. So we can use the impedance control, or we can use the variable stiffness actuator. But in this paper, we present a novel concept of the macro mini linear actuator. For macro mini linear actuator, we have the high force system as the macro system, and we top up by the low impedance unit. That we have a mini motor directly connect to the output, and also connect to the roll inertia rotor of ER fluid brake. And by controlling the impedance of the ER fluid, we can adjust the impedance between the high force and the mini system. So with no brake torque, the system, the endpoint can be driven by the mini motor. By moderate brake torque, we can adjust the impedance. And if the brake is completely locked, the system is going to be driven by the high force unit. So we can rapidly switch from low to high impedance. We always have the accurate position control at the endpoint. We have falling prevention. The end effector is going to drop down to the mechanical stopper of the carrier. And the brake just dissipate energy when we have the relative motion. We have macro, we have mini, we have ER fluid brake, and have force sensor at the endpoint. And in this video, it shows that when the macro system moves the carrier up and down, we still can control the impedance by the ER fluid brake. We want to have a low inertia rotor of the ER fluid brake. And we suggest that to have the multiple concentric cylinder that can machine separately and assembly it later, in order to have small radius difference between the inner and outer cylinder. We build the ER fluid brake prototype and characterize it. We adjust the voltage and we measure the torque output at a constant speed driven by the motor. And we found that we can see some torque fluctuation due to the inconsistent fluid gap by the machining accuracy. And we can see that it can track the positive and negative step combined with the response time less than 50 milliseconds. And when we plot the torque and the voltage, we can see that, of course, the torque increased with the voltage, and we can see the linear relationship. And at normal speed, actually, the torque doesn't rely on the speed, but at extreme speed, we can see the effect of the shear rate. And for the actuator, we try to plot the driving force required at different velocity. And by this way, we can estimate the static friction by observe the different or the torque shift or the force shift at zero speed. And of course, we found that maybe the static friction can be increased with the voltage of the ER fluid. For the slope of the force and velocity relationship, we can see the damping or the viscosity. The damping seems slightly decreased with the increase of voltage. We also implement a controller so that we can reduce the apparent parameter of the actuator. The static friction can be reduced when we increase the force feedback gain. And the inertia and the viscosity are estimated from the vibration test and fit with the linear second order system. So we also can see the reduction of the inertia and viscosity. And for static friction, it needs to be included in the model so that we can get the correct estimation of the viscosity. Thank you.